got his PhD from Princeton University, and he went to IBM research lab.
No, he was at Carnegie.
It's all in the details.
All right, this is what I know. I'm sure you know much more. And until John got professor position at CMU. So John is a statistician and also a computer science scientist, and he's doing all the way from writing theorems to writing algorithm to finding actual solution to real problems. I knew of this work, of his work from essentially his work on maximum entropy on the mean. He developed this beautiful method to build a model that was applied to language models. But today, John is going to tell us about exploiting sparsity and structure in parametric and non-parametric estimation.
Thank you, and it's very nice to be here. So I'd like to talk about some recent work I've been doing. It's mainly in the statistical vein. I'm going to talk about work that's mostly with my colleague Larry Wasserman in the statistics department at CMU. But there's also work with three of my students on the Buddy Kumar and Bill Dale, and some recent work with Martin Wainwright, and a former student with Jerry Judy.
Could you move the microphone up a little bit?
Yeah.
Stop it.
Is that? Okay. Good. So I'm going to talk about basically two areas of work that I've been pursuing recently. One is in sparsity in parametric and non-parametric settings, and also we'll talk about some recent work in semi-supervised learning. If I have time, and I expect I won't, I would say a little bit at the end about some recent stuff and trade-offs between computation and risk, but I don't think I'll get to that. So I'm mostly going to talk about sparsity and semi-supervised learning, but I'll give a little bit of, by way of motivation and background, some of the non-parametric inference. Okay, so at a high level, the basic name of the game in statistical learning is to balance bias and variance, right? So the basic bias variance decomposition says that the risk decomposes the square of the bias plus the variance, and we want to balance the two. But in high dimensional problems, that's very difficult to do. You can also think about learning as a coding kind of problem. And let me just say a little bit about this perspective. Okay, so for the regression problem, which is a lot of what I'm going to focus on, we have observed values, right? Those are the shaded dots. And those are unobserved evaluations of a function, the circles, the open circles, plus some noise. And we want to uncover the underlying function, right? So that's the function estimation problem. But we can view it as a coding problem. And I'm going to talk about most of the results in terms of minimax rates of convergence. Okay, so let me just remind you about what that means. So in the usual minimax view, so we have nature, right, as choosing some model, is represented by a parameter theta, and then data are generated according to that model. And then the learner estimates a model, theta hat, based on the sample, and then incurs some loss, right, the average loss or risk associated with the estimate. And the objective in the minimax framework is to minimize the worst case loss. Okay, so we want to minimize the worst case loss. And in a fairly general and precise sense, so the minimax risk is exactly equal to the information capacity of this viewed as a channel coding problem. Okay, so the minimax risk is basically the channel capacity. And so to view that as a coding problem, if you want to decode to a function, right, so you can just discretize the space of functions, right, by putting balls around a finite set of functions. And then you can decode to one of these centers. And then the minimax rate of convergence is exactly the rate of this code, right? So you take the logarithm of the number of these balls, divide by the number of examples, that's exactly the rate of the code, and Yang and Barron showed that the minimax rate is chosen to in such a way that the size of the balls, epsilon, is chosen to satisfy this equation. So that the logarithm of the number of examples, the number of code words divided by the sample size is equal to the squared bias. So this is the information theoretic view of the bias variance decomposition. Okay, so for various function spaces, then we have these well-known minimax rates of convergence. I'm mostly going to focus on standard Sokolov spaces. So we have a set of functions with some number of derivatives, and those derivatives have to be square interval. Okay? And then if we have say 2 derivatives in d dimensions, the minimax rate of convergence is n to the minus 2 over 4 plus d. Okay? So this is the cursive dimensionality. So when we're in high dimensions, this rate of convergence is extremely slow. So what I've done here is to plot this cursive dimensionality in for the Sokolov space of order 2, where we only assume the function has 2 derivatives. And then this shows the risk as a function of sample size, right? So to drive the risk below 0.1, we would need 1,000,000 samples. And here's the same plot viewed in a different way. So we're looking at sample size as a function of dimension to drive the risk below 0.01. Okay, so we see this exponential growth, which says that in 20 dimensions, theoretically, we would need this huge amount of data in order to get the average error to reasonable levels. Okay, so this is the cursive dimensionality. And so the main challenge in this area of machine learning and statistics, in my view, is to understand the theoretical and computational limits to learning sparse functions of this high-dimensional data. Right? Because if we're going to be able to learn in practical settings, there must be lower dimensional structure or sparsity in the target function, and we need to learn that structure and exploit it. Okay, so that's the challenge. Okay, so I'm going to talk about 2 recent results of ours in this general theme of learning sparse functions in high-dimensional data. One is parametric, and the other is nonparametric. Okay, so in the parametric case, right, the simplest setting is to just take a linear model. And so we have a linear model with a high number of variables in the model. Well, if we choose a small set of variables, we're increasing the bias in the model, but reducing the number of parameters, so decreasing the variance. But if we have a large number of variables, we decrease the bias, but increase the variance. So the bias-variance trade-off here is finding the appropriate balancing point. So one technique that is a very basic technique and has seen a lot of recent research is just L1 regularization. Okay, so in the signal processing literature, this was termed the basis pursuit procedure by Chen and Donahoe. It's called the lasso by Tibshirani in statistical literature. So we have the level sets of our loss function, which is squared error. So the level sets are these ellipsoids. Okay, and we want to minimize that risk subject to an L1 constraint on the parameters. So we restrict the set of coefficients to lie on this L1 ball. And the optimum then is typically achieved on a low-dimensional face or corner of this union of simplexes. And so that's geometrically how we achieve sparsity in this high-dimensional inference model. And so it's only in the past couple years that there's been a lot of progress in understanding this kind of technique from a theoretical point of view. So we can cast the problem in the following way as an optimization problem. We'd like to find the sparsest, we'd like to find the sparsest model, beta, that, say, achieves a risk that is below epsilon. Okay? But that's a intractable combinatorial optimization problem. So instead, we can do a sparse means L0 norm. So we want to find the smallest number of coefficients in a model that achieves risk less than epsilon. Okay. And so what the lasso does, or basis pursuit, is it relaxes this problem to a convex optimization problem by replacing the L0 norm by the L1 norm. And that results in this convex optimization problem that can be reasonably well solved practice. Okay, so there's been a lot of recent work in understanding this from a theoretical point of view. The story isn't over, but we have a much better understanding of it than we did, say, 5 years ago, even 2 years ago. Okay, so I'm going to talk about some recent work that builds on this. It's together with Ravi Kumar and Martin Wainwright, where the problem is to learn a graphical model from examples. I'll explain what I mean by that. Okay, so our work was motivated by this a recent result in the Gaussian graphical model case by Munchausen and Buhlmann. And there it's easy to visualize what's going on. So for a Gaussian graphical model, the structure of the graph is determined by the inverse of the covariance matrix of the Gaussian model. Okay? So learning the graph means to find the zero pattern in the inverse of the covariance matrix. So if we observe, if this is the graph over here, the true graph, this is a picture from their paper, we have this sparsity pattern which encodes the independence relations in the Gaussian graphical model. So by using L1 regularization, the lasso, where we regress each variable on the others, we're able to uncover a graph that has very few false positives. There are only these two false positives in that first graph, and the two false positives in that second graph. Okay. So what I'm going to briefly describe are recent results on carrying this kind of procedure out in the discrete setting, where we have just a discrete graphical model. Okay, so that graph those graphs don't show up very well.
The size of the data?
Yeah, well, I'll say more about the sizes in the experiments we ran, but in that example from the Munchausen and Buhlmann paper, I think those are 1,000 node graphs. And the
7 nodes, and how many samples?
The sample size is in the hundreds. But I'll give some examples in the discrete setting. I'll say more detail what they are. Okay, so those graphs didn't show up very well, but imagine we have some graph, right, on a set of nodes. We're considering undirected graphical models where the joint distribution of the random variables indexed by the nodes in a graph is given by the Hammersley-Clifford theorem as a product over potential functions, right? One potential function for each clique in the graph. So the problem then that I'm going to address is we have this graph, but the graph is unknown to us. And all we observe are these examples. Say we're in the binary case where each node is labeled either 0 or 1. So we have these labeled examples, and we want to, from those examples, learn the structure of the graph. That's the problem I'm interested in. And we're going to assume that the graph is sparse, in the sense that there may be many nodes, but there are roughly a constant number of edges per node. So in particular, I'm going to focus on the case of an Ising model, okay, where there are pairwise interactions between nodes in the graph. And the joint probability distribution then has this form, where the probability of a vector of ones and zeros is given in this exponential form. Okay, and one reason we're starting with this Ising model is this is identifiable. Okay, so we have a chance of uncovering the graph from data. Okay. Okay, so the model then is the following. So if we have this Ising model, this discrete graphical model, well then if we look at the conditional distribution of a node given all the other neighbors, all the other nodes in the graph, well by the independence relations, that conditional distribution only depends on the neighbors of the node. And then the distribution of the node given its neighbors has the form of a logistic model. So we can think of doing a logistic regression of that node onto its neighbors. Okay, but we don't know the neighbors. Okay, so the strategy then is to try to uncover the structure of the graph by doing a logistic regression of each node on all of the other nodes in the graph but then penalizing the coefficients with an L1 penalty, okay, in order to get sparsity. So that's the technique we're going to use. We perform this L1 regularized logistic regression, and then we look at the zero pattern in the coefficient vector. Okay? And we use that zero pattern as the estimate of the neighbors of the node in the graph. And now we are performing all of these logistic regressions. We want to uncover the entire structure of the graph. So we need all of them to be correct, and we need the error probability to decay exponentially fast, okay, because we want to simultaneously achieve all the correct neighborhoods. Okay, so that's the strategy. And our basic theorem is that this can be done with asymptotic consistency. So that is, in the limit, as the data size goes to infinity, we recover the true graph with probability 1 under certain conditions on the size of the graph relative to the sample size. And so in particular, and I'm simplifying this a little bit to make it a little more digestible here. Okay, so we have a sample size n, right? Those are the number of labeled graphs that we have as training data. And p is the number of nodes in the graph. Okay? And you can think of Dmax as a constant. That's the maximum degree of the node. Just take that to be a constant. Okay. So our theorem says that under certain conditions, if the sample size minus 2 log p goes to infinity and n times the square of the regularization parameter minus 2 log p goes to infinity, then asymptotically we recover the graph with probability 1. Okay, so this says that the regularization parameter has to go to 0 a little slower than 1 over root n, or log p over root n. And the number of examples has to be a little larger than 2 log p. Okay. So the sample size needs to get large, but the sample size can be relatively small to the size of the graph. Right? So it can be exponentially smaller than the size of the graph. And so what's allowing us to get this recovery then is sparsity. Right? Each node only depends on a small number, a constant number of neighbors. Okay? So the number of nodes can grow exponentially in the sample size. Okay? So that's the theorem, and it's now in this line of several results that have a similar nature in learning various types of models in the sparsity, in the parametric set. Okay, so here's an example where we generate graphs of size 100, 200, and 400 nodes. Okay, on the x-axis here, I've plotted the number of samples and the precision in reconstructing the correct neighborhoods. Okay, so we see here that the precision is high, but the recall is going up at a slower rate. Okay, of course, by changing the regularization parameter, you can make a different trade-off between precision and recall. Okay, but in the with the regularization parameter chosen as in the theorem, this is the performance that we get, and this is parallel to what I showed you in that picture for the Gaussian. Yeah. So the algorithm is very simple, right? So it's just penalized L1 regularization. So we take each node, perform a logistic regression of that node on all of the other nodes, okay, with an L1 penalty. And that gives us an estimate of the parameter vector for each node. Okay? We look at the non-zeros in that parameter. That is our estimate of the neighbors of that node. Okay? We do that simultaneously for all nodes in the graph. And that's the algorithm. That's the procedure.
How is it symmetrical?
Oh, okay, good. Yeah, thanks for asking about that. Right. Okay, so there are two procedures. This one I'm showing the OR. Okay, so you include an edge in the graph if it's included in any of the logistic regressions. Okay, or you could only include a node if it's included in all of the logistic regressions. Okay, that is a node in the okay, in this graph here, I'm showing that an edge is included in the graph if when I regress either of the endpoints on the neighbors, it's included. Okay? And in the end, you would demand that both of those logistic regressions include that. No, we just looked at those two basic decision rules for making the estimates.
Question?
Yeah.
Seems like these accuracies should be dependent on the temperature.
There's no temperature here.
No, I missed when you put up the equation for the icing model, but
Right. Because,
there's certainly a scale parameter which affects the degree of correlation between those that are connected with respect to the ones that aren't connected. Maybe you just left it at once.
well, we're estimating the parameters, right? So for a fixed setting of parameters, then you could scale with a temperature, right? But if you're just estimating the parameters, that scale is irrelevant.
Right. Every edge has its own weight.
Yes, every edge has its own. Yep. Okay.
Can I,
Yes.
I had some issue. I was surprised not to see anything related to some critical slowing down or something like that in the theory. So this is completely independent on, I mean, even if you are running the easing model with a uniform easing model with the same parameter for every node, you wouldn't have any problem in when you're close to phase transition, so large number of nodes and the parameter close to the critical conflict wouldn't happen.
Yeah, okay. Okay, so this question involves a little more. Maybe we could discuss it afterwards, but let me just give you the brief answer. So there are conditions here that I didn't put up, okay, because they're technical. And the thing you're expressing is going to come into those conditions. Okay, so in all of these results on sparsity recovery using Mellon regularization recently, there are incoherence conditions on the data matrix, the design matrix X, that need to be satisfied. Okay, and at a high level, what those incoherence conditions mean is that if you take any subset of relevant nodes, okay, those can't be too highly correlated with irrelevant nodes. Okay? So there's that kind of condition, which I haven't put up here. And if the true model is at close to a critical temperature, that incoherence condition may well break down. Yeah. Yes?
So is that why you don't have to do joint inference of the existence of edges? This is what gets you to decide on each edge in the graph independently of the other?
No, it's, I think that's a separate issue. Right, the theorem is fairly weak, right? It's this asymptotic consistency. You get that consistency whether or not you take the or the and. Okay? But of course, your precision recall is going to vary whether you use one of the other decision rules. Yes.
Yeah, related to the last question, I was exactly going to ask, why aren't we doing the joint implementation problem in the unique solutions supposed to do locally when we have paths and
Yeah. Okay. This is a good question too. So what you could do as well is you could use L1 regularized pseudo likelihood. Okay, and there you're jointly estimating all the parameters, and then you could use the same decision rule to estimate the graph. Okay. I imagine you could prove a similar consistency theorem for using L1 regularized pseudo likelihood. Okay, this is it's a weaker method, right? Because we're doing all these logistic regressions independently, getting different parameter estimates. Okay, but intuitively, the pseudo likelihood technique, should work better. Yeah. But and you'll get consistency that way. But we can't do joint inference, right? Because joint inference is intractable in the Ising model, and that's the point of this, right? You can't compute the partition function, and so we can't do joint inference.
Yes, you can. Many algorithms
Not in a general Ising model, not with mixed degrees, not in mixed.
yeah. Right.
In certain cases, you can, right? In a ferromagnetic case. Okay. All right. So that's a brief summary of those recent results. I have a lot of great questions on this, and I'd be glad to talk about this more. I want to get to the nonparametric results, which are really, I think, the main interest for myself. So we'd like to understand these theoretical and computational limits to learning sparse functions in the nonparametric case. And for this, we know much less. I think this problem is essentially wide open, and I'll describe what I believe are some of the first results in this direction. Okay, so in the non-parametric setting, what's the setup? Okay, so we now observe y as a noisy version of a general function, okay, of a high-dimensional vector. Okay, so the y is m of x1 through xd plus some noise. Okay, so d is large. We're in high dimensions, and we want to then estimate this regression function. Okay, but we have the curse of dimensionality. As I said already, if we are working in a Sobolev space of order 2, the curse of dimensionality says that the rate of convergence is 1 over n to the 4 over 4 plus d. Okay, so this is very slow. All right, well, what we'd like to do, though, is that for many problems, it's reasonable to expect that the true function is sparse. Okay? And in fact, as I've already argued, there has to be some sort of sparsity or low-dimensional structure in order to learn practically. And so, for example, in gene expression array data, right, the natural assumption in many applications is that the typic response, the disease of interest is only a function of a small number of genes, right? Although the measurements are of tens of thousands of genes. Okay, so we're going to assume that the true function is a function of a small number of variables. Okay? And the problem is we want to find what those variables are. Okay, so we need to do variable selection in this kind of non-parametric setting. So if we could isolate the variables, say there are of them, well, then we could get the faster rate of n to the minus 4 over 4 plus r, okay, which might be practical as far as small, like 2 or 3 or 4. Okay, so the challenge then is to do variable selection in non-parametric regression. Okay, the basic technique I'm going to use is local linear regression. Okay, so we assume that we can expand the function in a linear approximation, and then we estimate those coefficients locally. Okay, so we make a local linear approximation to the function. And we do that by estimating a weighted least squares problem. And we take a linear approximation and we weight the examples by their similarity according to some kernel function to the test point, the point at which we want to test, evaluate or predict. Okay, so in this method, we make we form this regression and solve this this problem for each test point. So the general situation with this kind of technique is that the kernel doesn't matter too much, but this technique is very sensitive to the choice of bandwidths. Okay, and this is very difficult in high dimensions to optimize the bandwidths. So the amount of smoothing is determined by the bandwidth, and that determines the shape of the local fit. So if we do too much smoothing, if the bandwidth is too big, we have a large bias. If we do too little smoothing, the bandwidth is too small, we have large variance. Okay? And so selecting the bandwidths in high dimensions is the problem. Okay, so what I'm going to describe is a technique we call rodeo for regularization of derivative expectation operator. And it's a general strategy for non-parametric estimation where we, in some sense, change the representation. So we regularize the derivatives, okay, as I'll explain it. And I'll give a very simple version of this procedure and a theoretical analysis that shows if the true function is sparse, then we do indeed get the optimal rate of convergence up to certain factors and therefore beat the curse of dimensionality in some sense. Okay, so the key idea is, at a high level, just a change of representation. So rather than working with a function, I'm going to work in terms of its derivatives. Okay, so we're just going to use the fundamental theorem of calculus. And what we do is we have a non-parametric estimator based on some smoothing parameters. Okay. We take the derivatives of the estimator with respect to the smoothing parameters, the bandwidths. And we have a greedy algorithm where we start with a large bandwidth for each dimension and iteratively shrink the bandwidths by just testing if the derivative is non-zero or not. Okay, so intuitively, if a variable is a true variable, if the regression function depends on that variable, well then the estimate is very sensitive to its smoothing parameter. Okay, so if I take the derivative of the estimate with respect to that parameter, that derivative should be big. On the other hand, if a variable is irrelevant, if the function doesn't depend on that variable, well then the choice of the smoothing parameter doesn't matter much, and the derivative should be small. That's the basic intuition. And so in a picture, what we're going to do is we're going to start with a bandwidth for each variable, and those bandwidths are all big. Okay, so we start with a high bias, low variance estimator. Okay. And then we compute derivatives, and we start to shrink the bandwidths when the derivatives are big. Okay, so the ideal path, suppose that we have two variables. We're working in 2 dimensions. Variable 1 is relevant, and variable 2 on the x-axis here is irrelevant. Well, then the ideal path would just keep that second bandwidth big and shrink only the first bandwidth down to some optimal point. And that's what we'd like to do. But our algorithm won't quite do that. We'll shrink the bandwidth for each 2 a little bit, but we won't shrink it too much. So that's the basic idea. Okay, so in a little more detail then, so we have an estimator, this local linear estimator. Okay, you can write it as a linear smoother. You can write its derivatives as a function of the bandwidths in closed form. And then we can estimate the variance of those derivatives. Okay, so the basic algorithm then is the following. And if you're familiar with wavelet thresholding for nonparametric regression, it's a little bit like wavelet thresholding. Okay, so what we do is we initialize all the bandwidths big, make all the variables active. Then we compute the estimated derivative, z, and its standard deviation, s. And then we do a test. We compute a threshold, which is s times the square root of log n, basically. And if the derivative is above that threshold, well, that's evidence that that's a relevant variable. We shrink its bandwidth. Okay? But if the derivative is below the threshold, we freeze its bandwidth at the current level. Okay? And that's the algorithm. So eventually the algorithm stops, because as we shrink the bandwidths, the variance increases. Okay, so eventually the variance for all the variables will be above, will be sufficiently large that these derivatives will all be below threshold. And again, it's similar to wavelet thresholding schemes. Okay, but we're doing this in high dimensions. And here's an example. So there's the true regression function, this highly nonlinear function with 2 variables. And this shows the average performance of the algorithm, where this is the step in the algorithm, and these are the bandwidths of the variables. So on average, the bandwidths for variables 1 and 2 are shrunk, but the bandwidths of the other variables for the irrelevant variables stay large. So this shows how we implicitly then are doing feature selection in this nonparametric model. Okay, here's another plot where here I'm varying the ambient dimension, d, okay, from 5, 10, 15, 20, running the rodeo algorithm and looking at the risk of the associated estimator. Okay, these are box plots of the risk. And you see that as we vary the dimension, the risk is staying relatively constant. On the other hand, if we estimate a single bandwidth for all the variables, but estimate it optimally using cross-validation, well, the risk is increasing. So we see the cursive dimensionality here, but the rodeo is able to effectively control it. Okay, and then the theorem is that, and under certain assumptions, but they're fairly weak assumptions, with probability approaching 1 in sample size, the bandwidths for the irrelevant variables are frozen to their initial values, and the bandwidths of the relevant variables get shrunk down to their optimal values, so that we get a rate of convergence which is near the optimal minimax rate of convergence, as if we knew the R variables in advance. So we get n to the minus 4 over 4 plus R rate of convergence plus epsilon. Okay, it's a little bit off. It's for arbitrarily epsilon bigger than 0. Okay? So, but now there's one other thing I should point out here, which is that this is a strong result in the sense that we're getting the optimal rate of convergence, but look at the dimension. So we assume here that the dimension d satisfies d log d is order log n. So essentially the dimension is order log n. And so we can't actually work in very, very high dimensional spaces. That's in contrast to those results I mentioned to you for the lasso, where we can work in essentially exponentially large spaces. So we can't do that here. And that's the trade-off we seem to be making in the non-parametric setting. It's unknown whether or not this is a fundamental limitation in the non-parametric setting. But there's very little known about this problem.
One quick question.
Yeah.
In the theorem, what happens if you have multiple relevant variables which internally are highly correlated? So in some sense, I'm thinking you're saying little r is the number of relevant variables. But again, just by accident, let's say two of them happen to be equal. So it's really not r.
You know, that's not a problem. That's not a problem here at all. I thought you were going to ask about something else, which is you might have an effective number of variables that's small.
Yeah, that's what I'm saying. So let's say linear transformation
Yes,
with r
exactly,
plus small
yeah.
dimension.
Okay, that's a good question, and our method doesn't handle that. Okay, so if the effective dimension is small, for example, after a linear transformation, that may well cause problems for this. Okay, so what we're assuming here essentially is that we're sparse in the original basis.
Or somehow you've done some, the variables are independent, the components of that.
No, but within the relevant variables, they can be strongly correlated. That's not a problem. Okay, but this rotation issue is a problem. Okay, and there has been a little work on this, and I can point you to it, but that's a very interesting problem. So yeah, it's a very good question.
Just
Yeah.
regarding the lasso, was it the same notion of dimension? The way
Regarding the
I don't
lasso,
remember very well, but I thought that the lasso dimension was the number of parameters. Am I wrong?
yeah, the dimension for the lasso is a number of parameters.
This is the dimension of the edge.
No, but this is not parametric, so this is infinite dimensional.
Yes, it's not related. This result is not. I mean, this is not the same dimension that we were.
Yeah,
You make
the hypothesis
lasso, I
space
just wanted-
is infinite dimensional here.
Okay.
That's right. But I was just pointing out that we can achieve this kind of result in much lower dimension, right? I would like that D is order n, but we can't achieve that. Not that you can achieve, D even exponential in the sample size, right? In our graphs case, in the parametric set. Okay. I'm going to run out of. Let me skip some things. There's a connection with Lars. If you see pictures that you're interested in, you can ask me afterwards. There's a way of effectively learning basis functions from data. So there's the famous Doppler function. If you apply this kind of technique, you automatically learn these functions that look like wavelets, but they're completely data-driven. So that may interest some of you. Talk about that. Let me say a little bit about density estimation. Okay, you can apply this rodeo technique, right? It's a general strategy. Right? You regularize derivatives. And you can apply it to other settings. So in particular, you can apply it to density estimation. And let me say a little bit about what that looks like. So first of all, what does it mean for density to be sparse? So it's kind of clear what a linear model or a regression function means to be sparse. But what does it mean for a density to be sparse? Well, one notion, which I think is maybe the natural notion you would come up with, is that the density is sparse if we can write it as a product of two factors. One is a function of only a small number of variables, and the other is very smooth, like a constant 1, or some other very, very smooth function. Okay, that's our notion of sparsity. So we're saying the density is sparse if it can be written in this form. And then the task is to, get lower dimensional rates of convergence in the dimension of this smaller factor. And we've developed the theory and algorithms for this for just simple kernel density estimators. So we take our kernel density estimator, which looks like this, but now we have these bandwidth parameters for every dimension. We can apply the rodeo algorithm and effectively choose the bandwidths and then beat the cursive dimensionality. And here's an example of this working. So these are, the data are just the scanned digits data. And the density estimation problem is to, given a test point like this 2 here, right, we want to estimate the density near that point. So we can use the kernel density estimate to do that. But when you run the rodeo algorithm, actually what I've run here is the rodeo in reverse. So we start with small bandwidths in each dimension and then greedily increase the bandwidths. And so you can think of that in the following way. So in the white space there of the two, right, everything is white, right? The density is pinned down to be 0 or white, right, at those points. Okay? So by having a very small bandwidth, you nail down that white space. Okay? Now, as you relax, you're going to see variations in the density by increasing the bandwidths in other pixels. And you can see that the features of 2s and nearby 2s in the local density emerge in this pattern of bandwidths, which is what I'm showing you in that right plot there. Okay? So the rodeo, in this greedy way, selects bandwidths, which are doing feature selection to pick up the features of the local density. And we get a similar rate of convergence in the theoretical analysis. Okay, so in summary for this first part, sparsity is, I think, a really important problem. If only because, as we're getting all these data that open up new opportunities for machine learning and statistics, many of them are very high dimensional. Right? And so in order to have practical learning algorithms, right, there has to be lower dimensional structure in the data, and we need to understand how we can uncover that structure and exploit it. And so I talked a little bit about parametric sparsity with L1 regularization, nonparametric sparsity. And again, I think the nonparametric sparsity is really wide open. These are some of the only results that okay. So the second, and I think last thing I'd like to talk about is semi-supervised learning. So the challenge here is to develop theoretical models and practical algorithms for semi-supervised learning. So I know a lot of you are familiar with this basic problem and have worked on it. There are kind of two basic frameworks, right? There are generative models and discriminative models. In generative models, it's kind of clear what to do, but in discriminative models, it's not so clear. There were two early results, one for each of these paradigms. There's a result by Castelli and Cover in '96 on a simple kind of toy parametric mixture model, okay? An identifiable mixture model, where they analyzed it and showed you could use unlabeled data to learn the mixture model faster. And then there was this paper by Blum and Mitchell on a discriminative framework called co-training, and there was a pack analysis of this. Okay, so these are some of the early papers that sparked interest in this area. Jerry Jew, who worked with me at Carnegie Mellon, is now at Wisconsin. He keeps this up-to-date survey of semi-supervised learning literature. And as of December, he had 163 references in this. And I'd say, there's been 10 years of work on this, and we still don't know what's going on with semi-supervised learning. Okay? There's a lot of methods out there, a lot of heuristics, but very little understanding of what's going on. So I want to describe some recent work on this. And the work is analyzing algorithms that are based on a use of a graphical structure imposed on the data in the following way. Okay, so this is a cartoon type of picture I drew to explain the idea where, imagine we want to classify digits. Okay, so each scanned digit that we want to classify, we're going to represent as a node in a graph. Okay. And then some of them are labeled, right? We know this one's labeled 0, that one's labeled a 9, that one's labeled a 1, but most of them are unlabeled. Okay, but we have a similarity function, right? We have some sort of similarity, like based on a kernel similarity that, well, this guy is pretty similar to this, and that's similar to that, and that's similar to this, and so on. And so the intuitive idea is to somehow propagate the labels throughout this graph. And a lot of the heuristics and methods in semi-supervised learning are based on this kind of notion that we want to use this graph structure and some sort of notion of smoothness of the target function with respect to the graph structure in order to use the unlabeled data. So the idea is that you construct this graph. You can think of it as a random field, and it encodes this intuition that similar labels in the graph should have similar instances, right, in the graph should have similar labels. That is, the function, the target function, should vary smoothly, But this could be, misleading, right? If the similarity function you use to construct a graph were incompatible with the classification task, this could actually hurt you. So, but here's one example of how these kinds of graphs in real data really do match this kind of intuition.
Yeah.
Yeah.
Distances mean how similar it is according to our similarity measure, is that right?
Yes. Yeah. Okay, so this is an example that Jerry generated, where what he did was he took this image data, I think this is just restricted to 1s and 2s, and you form this graph. Now each point is a point in 256-dimensional space. Right? And then you form the edges in this graph by just a Gaussian kernel. Okay?
Do you just take the nearest? I mean, everything has some similarity.
Yeah,
to
I
everything
think what he
else.
did here, Fred, was to just take the k nearest, okay, where k is some small number.
Right.
So it's k nearest neighbor graph. Yep. Okay, but now each point is in 256 dimensions. To visualize this, he just ran principal components and projected the graph into 2 dimensions. And this is the projected graph in 2 dimensions. So what you see is that, okay, well here's this region of 1s that are all similar, and it forms this kind of nice coherent substructure in the graph. Here you get the 2s with the loops at the bottom. Here's a 2s without loops at the bottom, and so on, right? So you can see there's a lot of structure in the graph, and it kind of matches the intuition, right? That the function should be very slowly changing over here. But if you look at the regression function, the probability of the 1 given x, right, it should be very slowly changing over here. Okay, so this matches the intuition, and indeed, these methods based on graph regularization work very well for these examples. And so there are, again, the graphs didn't appear there, but there are 2 types of random fields you could construct. You could have a discrete random field or something else. Okay, in the discrete random field, in the binary case, you treat each label on the graph as 1 or minus 1. Okay, you form a graphical model like an Ising model, okay, over that graph, and then you just do inference in the graph. Okay? And in this case, right, in the case where we have binary labels, and we're in the ferromagnetic case where all the weights are positive, calculating the most probable labeling amounts to a graph cuts problem. Okay? But in general, if the classes are not binary, it's NP hard to compute the most probable labeling of the graph, the discrete set. So what we do instead is to relax this discrete random field to a Gaussian random field. So we consider a Gaussian random field over the graph. And then inference amounts to just linear algebra. And there's a random walks interpretation of this where if you look at the posterior mean of the Gaussian random field conditioned on the labels, well, that's precisely the same thing as saying, well, if I start at a node and I walk along the graph randomly, choosing nodes according to the weights in the graph, well, what's the probability I hit a 0 before I hit a 1? So that's precisely the posterior mean of that Gaussian random field. Or another interpretation is as an electrical network. Right? If I form a network where the resistance of an edge is inversely proportional to the weight, and then I connect a voltage source across the labeled and unlabeled data, well, you can ask what is the voltage at one of these internal nodes? Again, the answer is precisely the posterior mean of this Gaussian random field. So this is just another view of this, which is well known from random walk theory. Okay, and this kind of technique works really well on examples like this image data, okay, or in text classification. So here's a result where we ran this on classifying documents, whether they're from the PC news group or the Mac news group. Okay? And this red curve, or the blue one, is using the semi-supervised technique that I just described to you. This dashed curve here is using support vector machine. Okay? So we can see that as a function of the number of labeled examples, we're learning much faster using the semi-supervised technique.
But that's easy because you only have to count how many times reboot.
Yeah, that was good. I don't think everybody else heard it though. The comment was that you only need to count how many times reboot here in about. Okay. Yeah, so the true function could actually be sparse. But we're not exploiting sparsity here, which is a very good point. Okay. But I should point out that why does this kind of example match our intuition? Well, intuitively, but I don't have a technique that would visualize this for you. I think it's reasonable to expect that you get these, coherent clusters in the graph, because in this newsgroup data, what happens is there's a posting to the newsgroup that quotes a previous posting, right? So that new posting is very similar to the previous posting because it quotes part of it, and that in turn is quoted by another posting. So if you did like single link clustering, right, you would get these long, thin clusters, and that's what the graph is capturing. Okay, and in these digits examples, it works very well as well.
What about new data point?
Yeah, that's a good question. So this kind of technique in this form is what some people would call transductive. So you're given the test set, and then you do inference over that test set. And if you get a new point, well, you have to start from scratch again. There are ways around that, and we wrote some papers on those, but you can just think of it that way, as transductive. Yes?
Can you go back to the previous slide? On the right curve,
Yes.
at first it goes down, that says, when the label set size goes up, actually the performance goes down.
Yeah, that's right. And the reason that happens is there's a different decision rule, okay, for using the posterior mean of the Gaussian field in that red curve than there is in the blue curve. Okay, and in a nutshell, you're better matched to the prior probabilities in that red curve. Okay, so if you have the prior knowledge that there are roughly equal number of Mac postings and PC postings, well, you should predict PC half of the time. So that's basically what's going on there. Okay, and here's another example where we have this video camera in the Coke machine in our lounge at Carnegie Mellon Computer Science Department. And we collected some low-quality webcam data of people in the lounge, and we want to do person recognition from this low-quality video. Okay, so the sampling rate is very slow in this video, and we applied this kind of technique where these two images are, that's actually Jerry there. So Jerry's there, and there's an edge between that image and that image based on color histograms. Okay? And there's an edge between this image and that image because they're close in time. But there's an edge from this picture to this picture of Jerry at a different day based on face detection. Okay, so we used we used a face detector developed in the Robotics Institute at Carnegie Mellon to do face detection in these images. And so you see that Jerry's face there, the profile, is similar to the profile here. So the faces are extracted, and then we do just a kernel similarity evaluation over those patches. Okay? That connects that image to this image. Then we have color histograms from this image to this image, and that allows us to then, by the random walk from this image all the way back to that image that was labeled. Okay, so this is another example of where this technique can work well. Okay, so we've seen, and there are a bunch of papers now on this, that these kind of techniques can work well. But why do they work well, and what's the theory behind this? There's very, very little known about this, essentially nothing. Was there a question?
Yes, in the previous example on the recognition, it was not clear to me what, in the semi-supervised framework, what were the label examples, what were the distance that you use when you say these two things are close, because the images that is not so well defined, but not so well. And then what was the task to be classified, new video sequence, or were the frames different data points?
Yeah, I can describe all that to you, and we have a paper I can refer you to, but just very briefly, I think we had 10 people. Okay, so we're classifying into a set of 10 people. Is it Jerry, me, Avram, or other number of people? And we constructed edges by these three methods, either color histograms, okay, or time, or face detection. Okay, so there are three types of links in the graph. And I don't recall offhand the size of the graph and the number of labeled examples and so on. I'm not quoting any accuracy curves here, but I can point you to our paper for that. But the technique worked pretty well for this kind of data, and much better than reasonable baselines that we compared to.
And how many examples do you have?
I don't recall offhand. Okay, so again, there's a string of papers on these kinds of techniques, all reporting good results on certain tasks. What's going on? So in particular, we can ask, okay, well, on examples like the ones I showed you, it looks like we're learning very fast. So we can ask, okay, in theory, do these methods yield improved minimax rates of convergence? Okay, so that's the question we asked, and the answer is no. Okay? So the rates of convergence are the same as if we only use the labeled data. So minimax theory does not explain what's going on. Or these methods just don't work theoretically in terms of those measures of performance. And let me say what I mean by that. Okay. So there are two types of assumptions people make in this general area. There's a manifold assumption, right, which roughly says that the distribution of data lies on some low-dimensional manifold. And that's one type of assumption. And then there's what Larry and I call the semi-supervised smoothness assumption, right, or SSS, which is that the regression function is smooth with respect to the data in some sense. Okay, and this is always vaguely stated in these papers. It isn't really said precisely what this means. But so the first result is that under the manifold assumption, right, if you just assume that the data lie in a low-dimensional manifold, this semi-supervised smoothness assumption is irrelevant. Okay? You can get the lower dimensional rates of convergence with just basic techniques. Okay? You don't need any of this semi-supervised stuff. And the second result is that, and I'll quote this more precisely in a minute, without the manifold assumption, the semi-supervised smoothness assumption is too weak, and more precisely, if you use one of the methods like I just described, using regularization based on graph Laplacians, you did not get faster rates of convergence. In order to get faster rates of convergence, you need to make other assumptions, and I'll describe to you some of the assumptions that we make. Okay, so our approach is the following. So let's let M, right? M is the regression function, right? If you're in the classification setting, that's the probability that the class is 1. So, and P here is the data density. Okay? So what we assume is we're going to assume that the smoothness of the regression function is some function of the data density in some parametric way. So in other words, we have some parametric set of maps that take a data density to a regression function, at least its smoothness parameters. Okay, I'll say what that means. And so we use all the data to estimate the density. Right? We assume we have lots of unlabeled data, so we can estimate this well. We use the labeled data to estimate this smoothness parameters of the regression function. And then we use the labeled data to estimate the regression function subject to these constraints on the smoothness. Okay, so let me explain what I mean intuitively. Suppose the data density looks like this. Okay, so it's locally Gaussian, but there's this kind of manifold structure. Okay? We're in 2 dimensions. The data density is still 2-dimensional, but it has this local curvature to it. Okay? What we're going to assume is that the regression function has a similar shape. Okay? So that if I overlay the regression function on top of this density, well, it has a similar curvature. That's the kind of assumption we're going to make. Okay. So now, what does regularization using these graph Laplacians do? Well, this is what Belkin and Yogi called manifold regularization. So we have the usual loss function for kernel regression, or it would just look like this. It's weighted squared error. But in addition, we regularize based on this term that in the limit, as the sample size goes to infinity is converges to the norm of the gradient of the function over the manifold. So that's why it's called manifold regularization. And this is essentially the same thing as we use in the methods that I described with Jerry. Okay, using, in the examples that I gave are essentially using this estimator. But the theorem is that this doesn't give faster rates of convergence. Okay, so if we take the usual kernel estimator, using only the labeled data, and let m twiddle be the semi-supervised estimate that minimizes that function I had on the previous slide, okay, then the ratio of the risks is bounded away from 0. Okay, so in other words, the rate of convergence for the semi-supervised estimator is exactly the same up to constants as the rate of convergence of the standard supervised regression estimate. Okay, so they converge at the same rate. Yes?
What is n the number of data points, and doesn't the result depend also on the percentage of training?
No, it doesn't actually. So, but we're assuming, of course, that the number of labeled points is going to infinity as well.
Yeah, but in what proportion relative to the total number of points?
Yeah.
Right.
You know, I'm not sure for this result, but I'm going to mention another result where I'll make that precise. You'll see what the trade-off
What
is.
the number of labeled points is 99%?
You'll see in a minute. Okay. So again, here's our intuition, right? That we have this data density that has some shape to it, and we assume that the regression function has a similar shape. Okay. Now, let's assume that the Hessian of the regression function, I mean by h here, is some parametric transform of the Hessian of the density. So for example, going back to that slide here, right, we could have that the Hessian is just some scaled version of the Hessian for the data density. Okay, so there are similar directions of smoothness, but maybe more smoothness. Okay, so we assume that it's a parametric transform of the Hessian. And now I'm going to assume that the number of unlabeled points, the logarithm of the number of unlabeled points, minus d, the ambient dimension, times the number of labeled data points goes to infinity. Okay? So I need, more than d log n unlabeled points. So I need two things. I need this amount of unlabeled data, and I need to estimate this parameter theta at a sufficiently fast rate. Okay, so suppose I can estimate this parameter at a rate that's n to the minus beta, where beta is bigger than the exponent for the Sokolov minimax rate. Okay, so you can sort of see where this comes in. Okay, so if these conditions hold, then the unlabeled data can help. Okay, if I look at this kind of oracle inequality, so this is the optimal risk, okay, and this is the risk using the labeled and unlabeled data versus using only the labeled data. So the difference to the oracle goes to 0. Okay, so in this setting, we can show that the unlabeled data help. Okay, and it makes precise the conditions under which they help. So that's the second result. And the third result, I'll just mention the idea. If you go back again to this picture I keep bothering you with, again, so it's that there's this local geometry of the density. Okay, so in this kind of picture, and the regression function, so in this kind of picture, along that ridge, right, or along those level sets, the density is very, very smooth. And similarly, the regression function is very, very smooth. Okay? So if we can identify those directions of very smooth behavior, then we can exploit them and then get faster rates of convergence than we could just using the standard coordinate system. Okay? And that's the third result. I'm not giving a precise statement of it there, but these are anisotropic Sokolov spaces. So in an anisotropic Sokolov space, and so locally, we have more derivatives in some directions than in other directions. Okay? So the task is to determine those directions. And we can do that using the unlabeled data, using density estimation. Okay? And then if we assume that the regression function has similar directions of smoothness, then we can exploit them and learn at a very fast rate of convergence using the labeled data. Okay, but it requires using the unlabeled data to find those directions of smoothness. Okay, so that's the third type of result. Okay, so I'll stop here just to summarize the semi-supervised learning problem in our results. So I think semi-supervised learning has, rightly been getting a lot of attention because it's a really interesting and important problem, right? There are many natural situations like speech, right, where it's easy to get unlabeled data. I mean, lots of it, but it's hard to get labeled. Okay, so there's potentially a big win here, but we really need to understand better what's going on and understand the theoretical frameworks because we have lots of heuristics now here, and they're unreliable. Right? There are some settings in which they work, and some settings in which they don't, and we don't have a solid understanding of what's going on. So this is our first attempt at trying to understand what's going on. Okay, so I'll stop there, and thanks for your questions, and I'd be glad to answer any more.
All right.
Yeah, thank you.